Hello once again, AP Calculus 80 students, Mr. Record here. We are going to have a discussion about how to find the derivative of an inverse function now. And if you are my students, I'm going to actually jump ahead to where example 6 is located in your notes. I often will refer to this as the method 3 procedure in which to find the derivative of an inverse, which is without question the most efficient way that one would go about doing this on the advanced placement test. In fact, I wouldn't recommend either of method 1 or method 2. If you're watching from outside of Avon, I will have videos posted that might describe method 1 and 2. But method 3 is sort of a foolproof method that's going to allow you to answer virtually any kind of question, whether it's written as an equation or written in a tabular type of method that you could encounter on the AP exam. So you've got the formula here in this box, the derivative of an inverse function. It says if f is a function that's differentiable on an interval I, and if f has an inverse function called f inverse, then f inverse is differentiable for any x as long as the derivative evaluated at its inverse is not 0. And moreover, we have this relationship that you can see in the box. Well, that's a pretty intense relationship. If you look at that, it's very easy for us to think, well, gosh, where's this coming from? And what I want to do is I'm going to use the space here down in example 6 because I want to keep the box there on the page. So I'm not going to actually do example 6 yet, and then I'll erase this prior to beginning example 6. But all I wanted to do is just kind of start from a very clear fact about inverses. A fact that you learned back when you were first venturing into the inverse function, and that is if you were to take an inverse and plant it inside of the original function, everything would cancel and you would just be left with x. Probably the easiest way to kind of think about this is, say, an arcsine function with a sine function. Another way to think about it is saying one function is x squared and another function is the square root of x. Those are inverses of one another. And if one is planted inside of the other, things tend to cancel out and you'd be left with only x. So we have to buy that particular fact. Now, once you know that, if you perform implicit differentiation on both sides of this equation, it will reveal that formula that I have circled. So we would think of it like this. Taking the derivative of f inverse of x with respect to x and doing the same thing on the right side, taking the derivative of x with respect to x. Now, if we look at the left side, in order to pull this derivative off, we have to use the chain rule. So we have sort of the outside function, the f function, and when we differentiate him, we would get f derivative, the derivative of f, still evaluated at the inside function. But then we owe it to ourselves to take the derivative of this inner function, the derivative of f inverse of x. And the way that we'll write that, it's a little bit different looking notation, but we'll say f inverse prime of x. And you can see how that's the same kind of notation that's used up above. That will be equivalent to, on the right side, the derivative of x is 1. So just take another good look at the left side. That's the part that typically bothers students. And all it is just the chain rule. Get your derivative of the outer function f, and then your derivative of the inner function f inverse. Next, all I'm going to ask us to do is to divide both sides by this particular expression. So that will leave the f inverse derivative of x alone on the left side, and then on the right side you would have 1 over f prime, the derivative of f, evaluated at the inverse, and lo and behold, that's exactly what we have in our formula up above. So that gives you a little bit of an idea about where this thing comes from that we're going to use quite often. So if I get rid of this, let's go ahead and start thinking about solving this particular expression. It says find the derivative of this inverse function, and we're going to do so specifically at x equaling pi, and we'll use the formula above. Now, one of the things that is a little tricky about this is the fact that whenever you're given a specific value, x equal pi, it's very easy for us to think, oh, that's an x value, pi. So we would plug that in for x and maybe find some f of pi. But we have to keep in mind that we're asked to find the derivative of the inverse when x is pi. So I'm going to kind of refer to that particular x in the formula as being pi. Now, since that is an x value in our inverse, it has to act as a y value before we take the inverse. Now remember, that's one of the key ingredients of inverse functions. An inverse function is technically defined as a function whose x and y values flip-flop from the original function. Of course, some certain conditions have to apply in order for that to happen, but essentially that's really all there is to it. So when we look back at this problem, what we need to do first of all, our first step, is to take the x value that's provided and let that take the place of the y. So we're going to say that the pi is equal to x plus sine of x. Now, when we go about solving this, this is a very tricky equation to solve. And a lot of times, if you're looking at a problem like this and it is without calculator assistance, there's going to be a pretty easy x value that you can probably find by trial and error. So, maybe you try different things. Like, well, maybe if you try to let x equal 0, maybe this is going to work. Well, I don't think that's going to be the case because pi does not equal 0 plus the sine of 0, right? Which is equal to 0. So that's not a true relationship. So you start thinking about some other possibilities. Maybe x is pi over 2, or maybe even x is pi. So if we try x being pi, well, then we would have pi equivalent to pi plus the sine of pi. Now, if you think about that, that is a true statement. Because the sine of pi is 0, we have something that has truth to it. Now, the one thing about this example that I'm not real thrilled about is the fact that the x value that they give us was pi, and it produces a result that's also equivalent to pi. That is just really a coincidence with the way that this problem is presented. But I want us to keep in mind that this equation does yield pi as an answer for x. Okay, now we're going to put that off to the side because that's actually going to take the place of this thing here in just a moment. And I'll explain how it does that. All right? So the very next thing that you need to do, step 2, is to take the derivative of your original function. Okay, well, that's not a very difficult thing to do because our f of x is a pretty well-behaved trigonometric plus an algebraic piece type of function. So the derivative of x plus sine of x would be 1 plus cosine of x. Generally speaking, that will be one of the easiest parts of these problems. And then step 3, well, step 3 is really and truthfully the final step. Because in step 3, you will take what's really the left side, which is what you're evaluating, f inverse prime evaluated at pi, and you'll set that equal to 1 over the expression you had for f prime, which is 1 plus the cosine of x. But now we have to evaluate that at this f inverse of x. And that f inverse of x happens to be this value that you found in step 1. Now, as I said, it can be confusing because we're about ready to take an x and replace it in a function that has f in it, which means you're thinking, oh, we're replacing a y up here with an x value. But remember, that's not really true because this x value is an x value for the original function, which means it's a y value for its inverse. And f inverse of x is thought to be acting as a y type of value. So this x that's right here is just going to get replaced with pi. Now what I'll do is I'll just write it like this so I don't have to erase it. And then when I evaluate, I have 1 over 1 plus the cosine of pi, which is going to be 1 over 1 plus the cosine of pi is -1, and then something really strange happens. We have 1 over 0. Okay, well, another curveball thrown into the mix. And if you recall, in our stipulation here, it said that if our inverse evaluated within our function f prime produces 0, then we do not have a derivative. And that's exactly what's happened here. If I erase all this, we can see that this was the part, that was 0. So it seems like we've done a lot of work here to come up with the conclusion that this function does not have an inverse at that particular point. And so we would answer it with the simple does not exist. Now that may not be the best scenario to kind of throw at you right off the bat, but I want to go ahead and push on and do another example. Do one example here of a function that does exist. So just so that we don't lose sight of this valuable formula, I'm going to go ahead and I'm going to cut it out so that I can refer to it. So I'll just use the camera tool and do just that. So this is going to be our working formula. And then we'll move on to example 7. And I'm going to paste that formula right here and sort of move it up here in the corner. Now this time, the directions say, find the derivative of the inverse function of f of x equaling this cubic when x is 3, again using this formula. So step 1, if you recall, is to take this value of x, which is 3, and not plug it in for x, but plug it in for the f of x, plug it in for the y. So you would have 3 equal to 1/4 x cubed plus x minus 1. So now we have to rack our brains here, and we have to think about how best to solve a pretty ugly equation like this. Now, there are some instances when the equation that you have is going to be so bad that you will have to use some kind of a calculator in which to do this. And you can do this on your TI Inspire. So I'm going to allow this to be a calculator active question. And rather than show you the calculator procedures to do this, because I don't have the calculator software on this particular computer, I'm going to ask that you guys go to your TI Inspire and basically input this command. I want you to solve the fact that 3 is equal to 1/4 x cubed plus x minus 1, and you'll solve that for x. Now, hopefully you've had a chance to do that. Perhaps you could pause the video. In any event, you will get x is equivalent to 2. Now, wait a minute, we didn't need a calculator for that. Could we have figured this out sort of by some other means? And the answer is yes. So if you do have a problem like this and you are not allowed to use a calculator, you have to understand that I, as well as any reasonable teacher, is going to ensure that the value for x is going to be a nice integer, and it's probably going to be one that you don't have to fish around too long to find. So what I would say, like I did before, is just try some various numbers. Maybe we're going to try and see if x equals 0 would make this a true statement. Well, I think it's going to be pretty clear that you're going to get 3 is equivalent to -1, which we know is no bueno. So then we'll try maybe x is equal to 1. Well, maybe this is going to work. Is 3 equivalent to 1/4 plus 1 minus 1? And I'm seeing that 3 and 1/4 are not going to be equivalent. So before we get frustrated, we want to just keep pushing on, just knowing that reasonably we wouldn't have to try too many numbers. Maybe 3 or 4 failed attempts would then lead to a correct answer. So let's see what 2 does. 2 is going to give us 3 is equivalent to 1/4 times 2 cubed is 8 plus x, which is 2 minus 1. If we continue to simplify this, we would have 2 plus 2 minus 1, and before long we see we have a true statement. Typically speaking, in my class, if 0, 1, negative 2, or 0, 1, and 2 don't work. Negative 1 and negative 2, one of those two will certainly work. So we've got our value that we need, so we don't want to forget this guy. So we go on to step 2, one of the easier steps, and that is just to take the derivative of our function f of x, which is 3/4 x squared plus 1. Now for the big part. We assemble our formula. F inverse is prime. So the derivative of f inverse evaluated at our 3 that we are looking for up here is equivalent to 1 over the derivative of f, or 3/4 x squared plus 1, evaluated when the x is now the answer from part 1 or 2. We continue to work this. We get 1 over 3/4 times 2 squared, or 4, plus 1. The 4's cancel, and we get 1/4 for our answer. So this is an example of a problem that does indeed have a derivative value of an inverse. Now I'd like to finish with this example 8 and show you what seems to be more likely the trend on some of the more recent AP exams, and that is to give the students a table of values. So you see that we have selected values of a strictly monotonic function g and its derivative g prime. They use that language just so that we know that this function that's monotonic, g, has an inverse. And you can see that part A says we want to find the derivative of the inverse of g evaluated at 1. Now you can still do this using the same step-by-step procedure. The only thing that I'm going to caution you this time is that a function that we're dealing with is g instead of f. So I wouldn't let that bother you. This is now what our formula would look like. Instead of having an f in my formula, I now have a g in my formula. Next, we're going to go ahead and do step 1, which is not using an x value of 1 in our function of g, but letting that be the y value. So what that means is you've got to go into your g row and look for a value that's 1. Once you find it, that corresponding x value is going to be the x that you're seeking. So since we know that g of -1 is 1, and hence we have a match here, the x value that we seek is -1. Now the thing about these kinds of problems is that there is no need to have step 2. You don't need to take a derivative of g because it already has been done for you in the chart. So you would move strictly to step 3 that I showed before, and that's basically using the formula up above, saying that g inverse prime evaluated at 1 is 1 over g prime evaluated at, and all of this stuff that I'm highlighting here in blue, this g inverse of x, this seemingly looking y value, is this x value that we found because they're inverse relationships. So we are going to replace the value in the parentheses here with -1. And so when we read this from the chart, g prime of -1 up here is going to give us this value of -1/5 down there. So I have 1 over -1/5, which gives us, of course, an answer of 5, or -5. Let's try one more here for part B. Again, the same idea applies. We're going to say in step 1, for g inverse derivative evaluated at -3, we're going to say g of what is equal to -3. We're going to let this be the y value. So I'm going to erase the information I've got here. I'm going to look in this g row. Where do I find a -3? And there better be one, because if there's not one, we could have some trouble. So we have this value. So we know that this value here must be a 4. So we know that x is going to be 4. We immediately go to step 3. And in step 3, we can pretty much just write what we're trying to find. The inverse of g's derivative, evaluated at -3, is 1 over the derivative of g evaluated at this number 3 that we found. Sorry, don't mean to confuse you. I wrote 3. I should have written 4. That should be a 4. And that's a good thing because there is no 3 up in this top row. So forgive me for that mistake. That should be a positive 4 from before. So it's 4 that we're going to plug in for this value. And then when we look in the chart, we see that the g prime is indeed equal to -2. G prime of 4 is -2. So our final answer would just be -1/2. Anyway, I hope this helps. You should, for my students, be able to handle pretty much the vast majority of the homework problems in the section 2.6. Anyhow, I will see you at the next video.